Okay, let's get started. Hello, everyone. Thank you very much for joining today's CGD seminar. I'm Jiang Zhu, host for today's seminar. It's my great pleasure to introduce David Clemens. David got his PhD from Dartmouth College in 2023. He was a postdoc with Marika with us for maybe a couple years. And David currently works at the University of Colorado Boulder and is a long-term visitor with us. And David works to improve predictions of changes in the Earth system with a focus on polar regions. He has done a lot of field works in both Arctic and Antarctic. He also works on model development, advancing process modeling within CSF. And David lives in Denver with his wife and a dog. He thinks he spends far too much time staring at computer screens. Today, David will talk about melt ponds on Arctic sea ice. Before handing over to David, I would like to remind people that please hold your questions to the question and answer session at the end of the talk. With that, the floor is yours.
Great. All right. Thanks very much, Young. Thanks for having me. Thank you all for being here. Obviously, this is a slightly different setup than how we typically do the CGD seminar. And so in order to keep using my mouse, I'll try to sit down. You may not be very functional there. All right. So today I'm going to be talking about melt ponds on Arctic sea ice. And so as a slight edit to what Zhang said, I'm actually going to encourage you to ask me questions during this, in part because my goal here is really to sort of, more than anything, is to introduce you to these features of the Earth system. And so I will talk about some of our science results as well towards the latter part, but what I've found in talking about melt ponds and in presenting results on melt ponds is often the first thing that comes up is people maybe haven't thought about the existence of melt ponds on sea ice at all. And that's quite reasonable, right? Most of us don't encounter them in our regular lives. Actually, a quick show of hands. Who here has seen a melt pond on the Arctic sea ice? Okay, so that's a much higher percentage than maybe I'd anticipated. How about stepped in them, walked through them? Okay, got a couple. Fallen through? No, okay. And so like I say, but that's a few of us have some experience seeing them, some experience maybe walking in them, but most people do not, including most of this room. So that's going to be part of my goal here. All right, one last quiz for the room. Does anyone want to take a guess of, at their summertime peak, how much of the Earth's surface area approximately melt ponds on Arctic sea ice occupy? You want to just call out or raise your hand? 4%. Okay, I don't have it in percentage. How about millions of square kilometers?
Here, put it in. Yes, a 0.1.
0.1%. Okay, I actually don't. So the approximately it's 2 to 3 million square kilometers, which I don't know how the surface area of the Earth off the top of my head, but for comparison, the like freshwater lakes on Earth occupy about 4 million square kilometers, and so it's not a negligible fraction of the Earth's surface area that's occupied by these features. Okay, so a quick rundown of where we're going to go over the next 45 minutes or so. First, like I said, I really want to provide you an introduction to what are melt ponds, how do they work, a little bit about why you might care about them. And then from that, we're going to transition into how we model melt ponds in SEIS and CSM2, and ultimately in CSM3. So I'll be discussing a new melt pond parameterization that I worked on during my time here with Marika. And then finally, I'm excited to bring you some ongoing research from fieldwork we've been doing this past summer, looking at sort of the next step of building a better understanding of melt pond properties that I hope will eventually get into SEIS and CESM, although it won't be for CSM3, maybe CSM 3.x something.
1.5%.
1.5%. Okay. So a little under 4%, a little more than I think Will said, 0.1%. So right in that ballpark. And like I say, please feel free to ask questions throughout this. I'd much rather you ask a question than, spend the next 45 minutes being confused about something because I didn't explain it well.
I have a quick one.
Yes.
Have you broken through a melt pond?
Believe it or not, I haven't actually, which I'm surprised by because I've spent a lot of time drilling in them.
I mean, I was afraid I would.
And then I had one question about actually was your title. You specifically indicated Arctic. Are they different in the Antarctic? And why isn't it included?
That's a great question. They are quite different in the Antarctic. And there's a couple of reasons for that. The single biggest one is that the Antarctic has much deeper snow. And so the ponds end up being buried under the snow. And so we simply don't see them in the same way, and they don't have the same impact on the radiation. And then the other factor that really dominates the Antarctic ice mass balance is that the ice gets melted out from below. And so you would think, okay, well, if the ice is melting from the surface, yeah, even if it starts with a lot of snow, eventually that snow will melt and it'll contribute to the pond balance. But actually, if the ice melts from warm water underneath, then the ponds never get a chance to emerge onto the surface. There are, however, features like melt ponds on Antarctic sea ice, driven by essentially wave action and water overtopping the ice. But I won't talk about them here. We don't model them. In fact, we have a handful of measurements, period, of them in general. But yeah, thank you for asking questions. That's it's much more fun for me too, rather than sitting here listening to myself talk. Okay, so what is a melt pond? Right, a melt pond is a puddle that forms on the surface of Arctic sea ice. So it forms due to meltwater collecting in depressions, just like they do on land. These melt ponds in general tend to occupy up to about 20 to 40% of the Arctic sea ice area. And so you can see, for example, in this mouse is really not going to work. Sorry about that. So in the image on the upper left here, this is an aerial image from this past summer of one of our ice stations. The ship in the bottom center is the Polarstern. That ship's about the length of a football field with the end zones. And so that gives you sort of a sense of the spatial scale of them. Additionally, the satellite images shown on the bottom right here, each of those squares is 1 kilometer on a side. And so spatially, individual ponds vary from the size of, about this table and smaller to roughly the size of hundreds of meters, at least in sort of their long dimension. In terms of their depth, most melt ponds on Arctic sea ice are pretty shallow. And so for the most part, you can walk through them, as we're doing in the upper right here, although you probably want tall boots or waders or maybe a dry suit. depending on the pond itself. And so there are places and locations where they do get much deeper. There's some great photos from Mosaic of people going into like meter plus deep melt ponds where they have water up to here and they're having to hold the instruments out like this to make measurements. Those tend to be associated with heavily deformed ice. And so they occupy a much smaller fraction of the surface than the sort of typical melt pond, which might be about shin to thigh high. And I already touched a little bit about why, I think you should care about them and that they're a significant fraction of the Earth's surface.
How can you tell from the imagery if it's a melt pond versus a lead? Was the question.
That's a great question. So I'm going to skip ahead for just a second to answer that, and then we'll come back here. The sort of short version is that the color and the shapes tend to look different. And so whereas leads tend to be linear features that have essentially ice edges bordering them, melt ponds tend to be surrounded by ice, and they have these sort of very curved shapes. And so the image in the upper right is showing some work from Nick Wright doing machine learning based classification of high resolution aerial and satellite imagery to pick out the ponds versus leads. But yeah, great question. Okay, so why do we care about melt ponds? Well, they actually have quite a number of impacts on the Arctic system. The one that we think about most as climate scientists tends to be changing the surface energy budget of the system. So melt ponds substantially reduce the albedo of the sea ice cover relative to bare ice. You can kind of, so for example, Nora and Savannah up there in the upper left image are using radiometers to measure the albedo of these melt ponds. You can just see the pond that they're measuring is much darker than the bare ice that they're standing on, right? It's going to absorb a lot more energy from the sun. It's also going to allow a lot more energy into the upper ocean. And so ponds serve as these sort of windows to the ocean through the sea ice. The image on the upper right here is a still capture from a video from Avi's remote operated vehicle, which dives under the ice to make various measurements. And the light area that the sort of claw of the ROV is pointing at, that's what a pond looks like from underneath. So it's much brighter than the surrounding ice. And that's just because the surface is darker and it allows more light to penetrate through. In addition to the impacts on the surface energy budget, the ponds also can impact the salt budget of the upper ocean. And so they do this in a couple different ways. Ponds essentially delay the delivery of fresh water into the upper ocean. So if the water is trapped in the pond, it can't be impacting the mixed layer. But also the ice under ponds desalinates more rapidly than bare ice. And so you actually, there's sort of competing effects that we don't fully understand the overall impact for. I mentioned the light transmission to the upper ocean. This is very important for biological productivity in the ocean, but actually the ponds themselves can serve as a niche for primary productivity. So the bottom left here is showing algal aggregates in a pond. Just to give you a sense of scale, the big aggregates here are a little bit larger than the size of my fist. And there hasn't been a ton of work on biology within the ponds themselves, but we actually found on the most recent contrast expedition, some of my colleagues at Avi found surprisingly high primary productivity within the ponds themselves, not just in the ocean water underneath ponds. Ponds also reduce the air ice and ocean roughness. They can change your drag coefficients, which is represented in SICE, but we don't typically turn on those parameterizations actually within CESM for various reasons. They majorly complicate remote sensing retrievals. As the question earlier, sort of key to this difference of, well, how do you tell lead versus pond? That can be a really major challenge, especially for coarse resolution satellite products. And then finally, ponds actually serve as an impediment to on-ice navigation. So if you're trying to walk across the ice cover, ponds are the most likely place you're going to fall through, essentially. If you're a scientist wearing a dry suit, like my colleague here, not a big deal. You just pop out and keep going. It would be a bigger deal if, say, you were carrying an expensive piece of equipment or you were trying to develop an autonomous system that could navigate over sea ice.
David, you mentioned on the previous slide that they delay the delivery of fresh water to the ocean. Is that advertised in SICE?
It is not actually. And so well, sorry, I should be careful here. In the level pond formulation and the sea level pond formulation, which we'll get to, which are the two that we use in CSM, the meltwater that's produced on the surface is immediately delivered to the ocean for purposes of mass balance. In the topo scheme, which I am unaware of that is currently used in coupled modeling, at least within SICE, it might be within SIQ. There is the option to actually withhold that water from the ocean. But at least for within the CSM context, that water is sort of immediately enters the ocean with no delay. Yes. Yeah, thank you for the question. Okay, so we've talked a bit about why you might care about ponds, about what they are. I want to discuss briefly sort of our understanding from actually decades of field work at this point on how they work physically. What are the physical mechanisms by which ponds form, exist, and then eventually decay or freeze over. So the sort of standard picture of these processes is well summarized by Hayo Aiken and others in 2004. And they break up the life cycle of a pond into 4 stages. Our first stage is we have the initial snow melt, the ice is cold, it's impermeable, water pools on the surface, and we get ponds that are generally suspended above sea level. In these cartoons on the left side here, these are cartoons showing sort of a idealized vertical section through the ice with the pond in blue, and I'm representing sea level by this sort of bad Microsoft Paint drawn wavy line. And so in stage 1, right, we form ponds just like puddles form anywhere else in the Earth system. Once ponds are formed, they immediately have a lower albedo than the surrounding ice. They have considerably more surface melt, and they rapidly melt down to the point where their bases are below sea level. Sometime during this process, which usually takes on the order of a couple weeks, we generate either macro scale flaws through the ice, or the ice becomes sufficiently warm that it permits percolation directly through the ice. And at that point, the ice is sufficiently connected to the ocean, that the ponds rapidly drain, and they drain down such that their surfaces now sit at sea level. And so this is stage 3 of melt ponds, is when their surfaces, their upper surfaces sit more or less at sea level. And then the ponds more or less stay there for the remainder of the summer. So once the surfaces are at sea level, any additional water that gets added simply drains away. And they'll continue deepening potentially, but they also can get shallower as well through ice deformation. Finally, the final stage of the ponds are that either their tops freeze over, and eventually the pond fully freezes and becomes part of the ice cover again, or the ice under the pond fully disintegrates and you no longer have a pond, you have a small area of open water.
So can I ask?
Yeah.
When do they ever become polynyas?
Do they ever become, I'm sorry?
Polynyas.
Ponds themselves generally aren't considered to become polynyas. Polynyas are essentially, the way I think of them, characterized by you have open water where you would otherwise think you should have sea ice. So they tend to be.
I mean, right?
Yeah, but they tend to be a cold that you have anomalous ice melt during the cold time of year when most of the ice around it is freezing. And so you have a polynya either because you have upwelling of warm ocean water that's leaving you to have open water, or you have strong winds that are basically like mechanically moving the ice away and repeatedly exposing the ocean. If we just have, say, a strong melt event that greatly reduces the ice concentration in an area, we don't normally refer to that as a polynya. Although perhaps there could be an argument for doing so in some cases. Yeah.
In observations, when a melt pond drains very quickly over like a day or something like that, does that imply that it was always above sea level, and that's why it doesn't go to this stage 2, 3 or whatever? You know, like it gets through the ice, but then it's dry because it was above sea level to begin with.
So actually, there's 2 different rapid drainage mechanisms that can happen. One is that the pond, had the positive hydraulic head, and it didn't have, it wasn't, as you say, it didn't have any, its base below sea level, and so a hole opened in it, either because a crack formed or maybe someone drilled a hole, as happens at times, and the whole thing can drain like that. The other mechanism that you tend to see actually quite a lot more later in the summer is that the base of the pond was at sea level, and the ice underneath it became sufficiently flexible that the ice simply floated upwards. And I can show you photos of this happening sometime later for anyone who's interested. That is a mechanism we do not represent in any sense in our models that I'm aware of, but it is something that you sort of see repeatedly in the field. Yeah, great questions. So this is obviously a somewhat complicated look at how ponds operate. Fortunately, however, when it comes to thinking about what information do we need for modeling them in the Earth system, there's a couple things that can let us really simplify this system. The first is understanding something about the timescales of these 3 phases, or these stages of pond evolution. This plot on the bottom right here is showing a compilation of several thousand very high resolution satellite images of sea ice and pond evolution. And so we're showing the melt pond fraction on the y-axis over time since the first time ponds were observed in a particular at a particular site. And I've highlighted in the bars here the three sort of primary stages of melt pond formation. The main thing to take away is that for most of the time, the ponds exist in this stage 3, in this red box here, right? That is the state for the majority of the summer. And actually, in terms of the melt pond fraction, at least as observed from space, even during stage 1 and 2, the melt ponds don't have that different of a pond fraction than what they have in stage 3. Right? So the ponds sort of tend to sit between about, call it 20 and 40% pond fraction, maybe 15 and 35%, depending on exactly where you're looking. And so what I will propose to you is that if we could have a model that does a good job of representing stage 3 melt ponds, that's a reasonable first step for an approximation of how we might model the ponds for the entire summer. And there's actually some pretty good reasons why stage 3 melt ponds should stay within this band of melt pond fractions. And the key point is, as I mentioned before, at this point, the ponds are connected to the ocean. And so the pond fraction is determined solely by the combination of buoyancy and the ice topography itself. And so we might have some really complicated true ice topography as shown on the left here, but we can actually represent it in a very simple way with just as this sort of idealized slice with a variable surface topography. And if we take this very simplified model, this actually gives us a tool to solve for, given the roughness, which I'm sort of characterizing here as the variation in surface topography divided by the mean ice thickness. We can actually use this idealized model to understand, well, what do melt pond fractions look like in stage 3? And so we get a curve that looks something like this over here on the right. And the key point here is that for the range of sort of really plausible roughnesses on Arctic sea ice, we end up with a pond fraction somewhere between about 15 and 40%. And so the really, really smooth ice, generally we can't get this because either there's small scale ice deformation and or snow dunes form on the surface of the ice. And so it's rare to get such totally smooth ice. It does happen sometimes, and on isolated occurrences, people have seen refrozen leads in particular that were very, very smooth and had no ponds on them throughout the entire summer. So this can really happen, but it's rare. On the other hand, in order to get such extremely rough ice that we would get this higher pond fraction, we're getting to the point where the base of the ice underneath the pond has to be so thin that it would be flexible and the ice would tend to equilibrate and smooth itself out, essentially. So there's some pretty good reasons why we might expect to see pond fractions in this realm. And so this will be the basis of what I show later on how we go about parameterizing ponds within SEIS for use in CSM3. Now, in contrast to how pond geometry tends to show this sort of nice convergence where we end up with ponds of about the same melt pond fraction, melt pond optics show really, really considerable variability. And you can just see this looking at photos of ponds from above, like this one here, where just by eye you can tell there's considerable variation between lighter and darker ponds. We can also characterize this quantitatively by looking at the albedo of ponds. In this case, I'll mostly present spectral albedos to you in this presentation. And so this is showing an example here of the spectral albedo as a function of wavelength for both ponded surfaces in the blue curves and bare ice surfaces in the red curves from Light et al. In 2015. And the main thing to take away here is that there's really considerable variability within these blue curves, within the ponded albedos, something like a factor of 4 variability. Now, Bonnie and others this was from a couple years of them driving around the Chukchi and Beaufort Sea making these measurements. But we can actually see such a similar magnitude of variability in optical properties, even within the same pond. So this is a really sort of impressively heterogeneous system at times. This is showing probably my favorite example of this from the contrast cruise, which was this past summer, where on the top here I'm showing the spectral albedo taken from a light part of the pond, which is this kind of the closer to where I was standing here. This relatively light part of the pond in the blue lines, and comparing it with the spectral albedo taken from a darker part of the pond, the same pond, in the orange line. And on the bottom here, just to show sort of what I was saying earlier about what you see on the surface in terms of albedo, you see the opposite underneath in terms of transmittance. And so the dark pond from the surface has considerably more transmittance underneath. Up to about 80% of the visible light is making it through this pond. Whereas the light pond from the surface is more opaque to radiation making it into the upper ocean. So we have as an Earth system modeler, this is sort of a maddeningly complicated situation to have, where on the scale of a few meters, you have such intense variability in the properties of the system. But I think there are some potential paths forward here, which I'll come back to at the very end of this talk. Okay, so before I go on to our modeling work, I just want to summarize what we've talked about melt ponds thus far. They form every summer on the Arctic sea ice, basically due to surface melt, getting trapped in depressions, and then deepening those depressions below sea level, such that once the ice becomes, or once the surface becomes hydraulically connected to the ocean, ponds persist on about 20 to 40% of the ice surface. We have a pretty good understanding of the physical processes that lead to that geometry, but they have really, really high variability in their optical properties, sometimes even within the same pond, such as the example I just showed. And this was one of my favorite ponds to look at, although I didn't measure it because the variability was too small for the footprint of the actual instruments we used to measure. And so that's sort of the summary of where we've been. Are there any questions about sort of melt ponds generally before we talk about briefly talk about how we model them?
Yeah. Bright versus dark areas, does that depend on the thickness of the ice underneath?
That's a great question. I'll ask you to hold that until the end of the talk, because we'll come back to that.
Okay,
Yeah.
guys, a quick question about the temperature of the water.
Mm-hmm.
Is that above freezing or below freezing?
So as with all, it's generally right around freezing, and it actually can be quite hard to measure really precisely at that point. Yeah, it is possible to develop some thermal stratification within ponds, but there is not much. And it's really, really hard to measure these things because the solar heating of your temperature probes themselves can have meaningful bias on how you make the measurements. Yeah, good question. Okay, so let's talk briefly about melt ponds in SEIS and CESM. I want to start with some comparisons between the observations we made on Mosaic and essentially the same a grid cell from roughly the same location within the CSM2 tuned ice ensemble runs. The top plot here is showing a comparison of the melt pond fraction between field observations, which are shown in the solid lines. I'll mostly focus on the Mosaic and Sheba observations in the blue and the red, respectively. And that's comparing with the melt pond fraction from CSM2 output, which is in the fainter lines with the uncertainty bars around them. And the first thing that I think jumps out to me is that CSM2 is simulating a much more extensive pond fractions than what we see in sort of field observations, at least on ice field observations that we see. So the ponds are too extensive in the model. You say, well, maybe that's not great. But then we can also go and look at the albedo of those ponds, which is shown in the bottom left here. And we see that, and this is comparing CSM2 again, now in the box and whisker plots, with just the range of albedo observed from on-ice measurements at Mosaic. And the thing that jumps out is that actually, compared to the field observations, the ponds in CSM2 are considerably brighter. They have much higher albedos than what we see in the field. And as it turns out, these biases offset almost perfectly in such a way that the grid cell mean albedo for the ice area within CSM2 more or less perfectly matches what we observed at both Mosaic and at Sheba. And so that's shown in the overlap here on the plot in the bottom right. So, all right. Grid cell mean albedo is okay. Why am I talking to you, David? Why do you care about about trying to get the pond area or the albedo more consistent with observations? Well, I'll give you at least 3 reasons I think you should care. First is as everyone's aware here, there's no guarantee that those errors will keep offsetting in a different climate state, in a different sea ice state. Second, there's been a lot of work going towards using data assimilation of different observables of the Earth system. Pond area fraction is a really good observable, but you can't use it for data assimilation if it needs to be biased to balance out an albedo bias. And finally, I'm going to highlight albedo is not the whole story here for the Arctic system. And so it's possible to have the same albedo, but very, very different light transmission into the upper ocean, which could have impacts on the ecosystem and on other aspects of the Arctic. And so if we want to understand why is it that CSM2 is coming up with such different pond fractions than what we observe in the field, I think it's really important to understand the physics of how ponds are parameterized, in this case using the level pond parameterization in CSM2. And I won't go through this in sort of the exhaustive detail that Marika's gotten to hear. I don't know how many times at this point. But the point I really want to highlight for you is that in the levelized parameterization, ponds are essentially always perched up above the sea level. It never allows the existence of ponds with their bases below sea level. And so that results in ponds that are essentially always draining and kind of always spreading out due to some other aspects of how the parameterization works. And so without representing the interaction between pond geometry and sea level, I think it's really hard to get the correct behavior. In terms of the optics, like what is causing that difference in albedo I showed, part of this is actually related to a choice that Bruce Brigleb made when implementing the Delta Eddington code. within SICE that essentially for shallow ponds ends up making them brighter than we would otherwise think they should be. And that choice might have been reasonable for data from Sheba, but the combination of the changes in geometry that the levelized parameterization causes with this choice to essentially smooth out the optical properties is resulting in these incorrect albedos. And so for CSM3, our goal was to update the melt pond parameterizations to do a better job of matching observations. And ideally to match the observations for sort of closer to the right reasons physically. That said, we really like the grid cell mean albedo evolution that you have in CSM2. And so part of the goal here was to not degrade that while we were trying to improve the physics. And so to do this, we've done two things. First off, I mentioned the choices made about essentially smoothing albedos for shallow ponds. We've collected more data on albedo over shallow pond, and we basically don't think those are reasonable choices. And so we've reverted to a version that results in considerably lower albedos, even for ponds that are 10 centimeters or less in depth. Second, in terms of the physics, we've implemented a parameterization called sea level ponds that explicitly represents the variability in the ice surface topography and allows that topography to be below sea level, and uses that in the calculation of the pond drainage. And so when we put these put this new parameterization to the test, we've tested it in essentially three different contexts. The first is doing a single column model. And so we can take out just the column physics within the SICE sea ice code, run it as a Lagrangian drifting grid cell following the Mosaic expedition, and force it with the observed atmospheric and oceanic conditions from the Mosaic expedition. And this gives us what I will argue is probably the best apples to apples test we can of the physics within the parameterization itself with real observations. The plots on the left here are showing some output from those comparisons and from those simulations. The top plot is showing the pond area fraction. The bottom is the pond depth. This is comparing with real field observations, and so we don't have the observations all of the times we want. We're not necessarily covering all of the ice types we'd like, but still I think we can do useful comparisons. The observations themselves are shown in the black line with the dots, showing the dates on which the observations were made. In this case, these are observations from a 3 kilometer long transect of snow depth, ice thickness, and pond depth that was repeatedly made on Mosaic. And for a direct comparison with those observations, we have the blue simulations. The dashed line is showing what happens if you use the level pond parameterization, which is the one that was used in CSM2. The results don't necessarily look so bad, but it's key to remember that because these observations only started on June 30th, we're actually initializing quite a bit into the melt season. You can see this sort of worrying behavior where the pond fraction just keeps increasing and increasing and increasing. If instead we had started the simulation back before the onset of the melt season, which is shown in these in the red lines here, by the time we reached this point in the melt season, that parameterization would have actually produced 100% pond fraction. And there's some additional nuances here I can go into. For comparison, the sea level pond parameterization, which is shown in the solid lines, does actually, to be honest, to me, surprisingly good job of tracking the observations. The parameters chosen here weren't tuned based on these observations. They were actually based on satellite images that I showed earlier. And so the fact that it matches so well with this specific set of field observations was sort of a nice coincidence, but probably more coincidence than anything else. One of the other nice things you can see is that with the new parameterization, even for running the simulation the whole year on quite level ice, which is in the red lines, we don't get these sort of unreasonably high pond fractions. The pond fraction stays within about the range that we see in field observations. So we think the parameterization does pretty well in the standalone configuration. We've also done standalone global simulations. We're running just the sea ice model forced by the atmosphere and the ocean. These plots here are showing the difference in ice thickness between simulations in these simulations with the parameterization, the new parameterization sea level ponds, and with the previous one, the level ice ponds. And you see basically nothing on these plots. And the reason for that is because the new parameterization is not altering the grid cell mean albedo in standalone simulations. And so we're not changing the ice mass balance, again, in these standalone simulations. And that's a good thing. That was one of our goals with the parameterization. However, as probably everyone in this room was very familiar with, when we actually put this into a fully coupled model and combine it with a responding atmosphere and ocean, we do actually see big changes in the mean ice state. And so we end up with, these are, I don't remember which tag of the model this was. So this is a very, was a development run back from in the spring, again, showing the differences on the right between the sea level pond and the level pond parameterization. And effectively, we end up with a much thinner ice cover with the sea level parameterization. And probably a big reason for that is that we have considerably more shortwave penetrating through the ice into the upper ocean, which in a fully coupled simulation can now feed back and impact the ice mass balance. So that's really a sort of whirlwind tour through the new parameterization and what we're doing within CSM3. And we'll have, those results are very preliminary and in development runs. I'm very excited for us to have sort of a workhorse configuration with a lab C not freezing over, that we can then repeat this analysis and get a better sense of the impacts of the parameterization change. I think in the interest of time, I'm going to go to jump. I'm not going to take questions here and just show some really quick new results, and then we'll have some time for questions. And you can also ask me things at lunch if you want. So what I've shown so far is mostly focused on changing the sort of physics of how pond geometry works and the mean pond optical properties. We haven't talked really about the variability that we showed at the beginning that Bill is asking about. And the reason for that is essentially that we need to do more field research to understand why and how much variability is occurring. What are the physical processes driving it? And so I was really fortunate to have the opportunity to do some of this work this past summer on the contrast expedition, which was a research cruise supported by the Alfred Wegener Institute. And on this cruise, I spent basically a lot of time making optics measurements in melt ponds and also taking ice cores out of melt ponds so that we could take a detailed look at the physical properties. And so the first thing we could try to look at when we see this type of difference in the pond optics is we might think, oh, well, maybe it's the depth of the pond, right? Maybe just the water, right? In our sort of regular life, deeper water tends to look darker than shallower water. And actually, as it turns out, in this case, that's not the case. So the NE pond, which was the lighter portion of the pond, the blue lines over here, NE pond actually had deeper water on top of it than S pond, which was the darker portion. So it's not the water depth. And generally speaking, that's consistent with observations throughout the Arctic. Could it be the ice thickness? Well, maybe a little bit. As Bill asked, in this case, NE pond really is a little bit thicker than S pond. That said, my suspicion is that the reason NE pond is that little bit thicker is simply because it has a higher albedo. It's not melting quite as rapidly, and it's not the underlying ice thickness. I would guess actually started out quite similarly. You also just don't really expect a difference of 8 centimeters of ice to change your albedo by a factor of 2. That would be a bit unusual. But one of the advantages of being on this cruise is that we could actually go and look into other properties of the ice. And so, for example, the plot on the bottom right here, I'm showing the density of the ice cores taken from field measurements. This was work that Dmitry Devine really sort of made possible. I'm really thankful for him that we were able to do this. And one of the things you see is that in the NE pond, so the blue curve, the ice sort of stays low density deeper into the column. One of the primary ways ice gets less dense is because it has bubbles in it, right? Bubbles serve as scatterers. They themselves can change the optical properties. So that's kind of a hint at maybe where this is going, why the ice might be different. The other thing we can do in field observations is that we can actually look in the core properties themselves. And so these two diagrams on the right side are showing ice cores on the left, vertical thick sections taken, so essentially a slice out of that ice core taken and mounted on a glass slide and photographed, and then those same slices photographed under cross-polarized light. And although these aren't the greatest images, this ice is quite fragile and hard to work with. You can kind of see just even in these that the ice in the NE pond, in the lighter portion of the pond, has considerably more bubbles, and also has more variation in the texture that we observe under cross-polarized light. You don't have these nice long vertical columns of ice as shown here for S pond. And the sort of primary hypothesis here is that this is actually a signal of ice deformation. And so when you have deformed ice, you end up essentially creating more granular ice. You end up burying the snow, you get more bubbles, and you could get this more highly scattering, more reflective pond ice bottom. And that's a really interesting hypothesis because that's something we actually represent in the model. And so there's actually a pathway to maybe having a ice deformation based optics parameterization. The other thing that we looked at is that in general, multi-year ice versus first-year ice tends to just look different, both in its albedo and in the physical structure. And so we wanted to understand, is this just because multi-year ice tends to include deformed ice or not? And so these are showing sort of a comparison of similar thicknesses of multi-year ice and first-year ponded ice. And what we see is that actually, even though all of this is columnar ice, so it's not deformed ice from what we can tell, the multi-year ice still is brighter. It still has more bubbles incorporated into the structure. And I think it'd be really interesting in future work to explore why exactly do we get these bubbles? How do we get them? Could that be parameterized within within the SICE model. And so this is just, I mean, you know, this cruise just ended about a month and a half ago. And so this is very much new results, but this is where I'm hoping we can go in the future with better understanding the pond physics and the optics. And there's potentially climate changing impacts from this, right? As people probably know, the Arctic is transitioning from multi-year ice to first-year ice. And so if there is a change in the optics associated with that, that in itself could feed back on the climate. Oh, and I just included some photos of the slides themselves, just because they're also one of the joys of doing this kind of work is the ice can be quite pretty. Okay, so I think I've probably gone almost over time. Just to sort of highlight the key points here. From our ongoing research, we think that sea level ponds does a good job of achieving our goals in terms of it improves the physical realism of pond processes for CSM3, but it doesn't appear to degrade the albedo evolution, at least in standalone simulations. As I said, I'm very excited for following up with more work in CSM3 to understand the impacts in the coupled simulations. And finally, looking towards the future of melt ponds and optics, I think we have some preliminary data suggesting linkages between the variability in pond optical properties and physical properties of the ice's history, such as the deformation history and the ice age. I think that will hopefully be fruitful directions to better understand this system. Thank you all very much for listening. I know we don't have much time for questions, but I will be in the lunchroom later and happy to chat further.
Yeah, unfortunately, we are running out of time, and then you can email Dave. And also, I think your office is in the 100 suite, right? Yeah. Okay, just try to find David if you have questions. And thank you very much for joining. And thank you, David, for the nice talk.
Thank you.